Good work. I'd like to talk about volcanoes again, and today I'd like to introduce you to the not so nice side of volcanoes. We've heard about the good side of volcanoes. I started with that, and today I'd like to introduce different types of volcanic products and also different volcanic hazards. So let me start with the concept of what people call the volcano magma system. Volcanoes are usually cone-shaped near or on the Earth's surface, and we think that's the main part of the volcano, but it's actually not true. The much larger part, like with an iceberg, is actually underground. We have a system of feeding chambers and conduits, and they go all the way through the crust. People talk about transcrustal magma supply systems, and then we go into the upper mantle, and usually that's where the source region of the magma is, and this may be several hundred kilometers down. So the actual feeder system and supply system of volcanoes is much, much larger than the volcanoes itself, and only a fraction of the material actually ever erupts. Most of the magma that's fed through the subterranean areas is getting stuck and is emplaced underground. So we never get to see it unless we erode it many million years after the volcano has ceased its activity. So, but let me start with this plot, and this is from the Smithsonian Institute, and this is one of these urban legends that I get asked quite frequently, and this is why I put this plot very early on. Now, if you look at the upper curve on that plot, that is the number of recorded volcanic eruptions. And it does awfully look like that there is more volcanic eruption as time goes on. But if you look very, very carefully, you find that there seems to be a dip in volcanic activity, particularly in World War I and World War II. And there seems to be also an increase in volcanic activity after big eruptions have occurred. And that tells us something is not quite right with that interpretation. It is that when people have had an experience of a big volcanic eruption like Krakatau 1883 or Pelée 1902, then people are more alert about volcanoes. And then they find volcanic eruptions or are aware of volcanic eruptions even in more remote areas. In particular situations where humans are busy with other issues, like in big conflict situations, then volcanoes become less of an issue, and there's less reports of volcanoes. It's as simple as that. And in addition to that, we have much more sophisticated monitoring tools, and these days we are just more aware if there's a volcano erupting somewhere in the high Andes, and in the centuries past, these may not always have been reported. The curve in the lower part is very interesting, and that is the intensity of volcanic eruption. And you see the red kind of, wiggly line there in the lower part from 1800 to present day, and it doesn't change very much. And that's a good indication that actually there is a continuous volcanic background scenario, and it's not changing. So we had no huge spike of intensity, and likely we also have no changes in terms of increasing numbers of volcanic eruptions. So, and if we look at this here, the known historical active volcanoes is also increasing together with the number of the eruptions that we record, and therefore it's a legend that there's more volcanic eruptions in younger history, in younger Earth history than in the past. There's good reasons for why we're recording more, and that's really the story there. So let me move on now. So today I'm going to talk a little bit about the background of volcanoes. I'm going to talk about direct hazards from volcanoes, but also then followed, I'm going to talk about indirect hazards, and then we'll close with a little bit of volcano monitoring and hazard mitigation considerations. So here, let's start. This is an image of Mount Vesuvius in the Bay of Naples. Some of you have probably been there. And here we have to recognize that volcanoes have direct and indirect effects. Direct effects are pretty obvious. If there's lava or ash coming from a volcano and you're affected, that's a direct effect. But many of those things have knock-on consequences, and that's the indirect effects. And we talk about those later in the presentation as well. And the key goal that volcanologists are really focusing on is the mitigation of volcanic hazards and the reduction of volcanic risk for the population. So here we have a little diagram that gives us the direct and indirect consequences. If you have an eruption right when the volcano blows up, within minutes to hours, you have obviously effects of ash clouds, of lavas, of all that kind of thing. And this is in a distance of a few kilometers. You can have indirect effects. They can follow days to weeks afterwards, and they can affect several hundreds of kilometers distance from the volcano. And then further away and further away in time as well, you have effects that may actually cause disruption of infrastructure, and ultimately you even have climate effects. You may have heard about volcanic winters, for example. That's when the temperature drops, for instance, after a large volcanic eruption. You may have heard about the year without a summer after the Tambora eruption 1816, which had strategic consequences in Europe, for example, because several of the rivers were frozen over in times when it wasn't expected, giving certain advancing armies advantages that would otherwise not have happened. So these volcanic eruptions and their climate effects, they even impact history. But let's talk about direct volcanic hazards first. And here, well, volcanoes pose direct risk. And here's a few images from Hawaii, for example, but also from Etna and from La Palma in the top right. And here, infrastructure is the main problem when we have lava erupting. Lava is usually not too fast, and it can often be outrun, but anything that's in its way that you cannot move is, of course, a problem. So the death toll of volcanoes falls heavily in just a few regions. In the northern hemisphere, you have very, very few people dying from volcanoes. But in the southern hemisphere, we have a lot more. And this is partly because we have a lot more dangerous volcanoes there, but partly also because monitoring efforts are not quite as advanced. So, therefore, here in Europe, not a lot of people are actually dying from volcanoes, and this is a good thing. And there is also two main types, which Katja and Maurice Kraft, you may have heard, two very eminent volcanologists in the 80s and 90s of the last century. They distinguish between two types of volcanoes, the black ones and the red ones. And the black ones are nice volcanoes, and the red ones are not. So let's start with the nice volcanoes. So here's a picture of different volcano types and different eruption types, and the nice ones are what people call the Hawaiian or the Icelandic type. There's no big eruption clouds, there's lava flowing out, and you may have a lava lake or features like that, but you can actually go reasonably close and you can admire them. But then you have other eruption types like the Vulcanian type or the Pelean type, and I'll talk about the Pelea eruption a little later, or the Plinian type, and these are much more dangerous. The Plinian type goes back to Pliny, the elder, who described the eruption of Vesuvius in 79 AD, and he also witnessed the destruction of Pompeii. So this is the worst of volcanic eruptions that we can have. So if you say to a volcanologist, a Plinian eruption, then we all go, oh, that kind of thing. So, black volcanoes, the nice volcanoes. Well, basaltic lava, that's what makes them black, is a low silica magma. And it's usually restricted, the effects are usually restricted to very near the eruptive center, maybe a few kilometers, in the best of cases 10 kilometers or so, but usually not a lot further. Etna has this type, Iceland, Hawaii. The lava flows occur at many volcanoes, of course, and they can affect infrastructure, and they can often also affect agricultural land and the communities that are in the way, but they're generally not a huge problem for the population. People, actually just yesterday, people frequently ask me, and yesterday I had a person coming up to me asking, so how long does it take for lava to become useful land again? And well, there was a study at Etna. It takes about 900 years if you have enough moisture. If you have a look at the Timanfaya lavas on Lanzarote, there was the first lichen and mosses on them, and they're 300 years old. So there is now colonization of the lava going on, but it takes quite some time. So it is geological time we are talking to make lava into fertile soil. And the Spanish have a term, they call it mal país. The fresh lavas are often referred to as mal país, the bad lands, because you can't really do anything with them. They're just in the way until they have decayed to soil and become useful. So here's a few impressions. This is Pahoehoe lava from Hawaii, and this is a Polynesian term. And there is debate exactly where the term comes from. Some people say it's so smooth that you can walk on it with bare feet. But then if you ask people in Hawaii, they say, oh no, it describes the ocean surface that's very smooth on a calm day. So in any case, what it says is smooth surface lava. And the surface gets smooth if it flows very nicely. The type of flowing that you see here, often it cools at the surface, and it's a steady flow underneath, and sometimes you make these wrinkle ridges on top. The image here on the left is actually from the island of El Hierro, and the other images there are from Hawaii, and there you see it in the formation. You see the little wrinkles forming on Hawaii, on the Hawaiian example there on the right, and a cold version of this with my old backpack here on the left. So, and these lavas, they can actually flow in channels, and sometimes the channels freeze over. You have a colder crust, and then you make these lava tubes or lava tunnels, and then they can flow for quite some distance. But it's a very restricted flow, very narrow usually, and only if they spread out in flat areas, then you get what we call lava deltas. They affect wider areas. Otherwise, it's a very narrow stream of lava. So here is a vent or the exit of one of those lava tunnels on Hawaii, and you see the geologist there for scale. Well, I'm not sure the hardhead will really save him if there's a collapse of this area, but he is obviously very brave and admires the exit vent there, and you see how the material is now exiting the lava tunnel there, and you see these bits of crust that are partly breaking up when the lava is flowing. So this is the lava lake in Hawaii, and there every now and then you get a little bit of a burst, and here's one of those captured in a photograph, and these lava lakes are depressions filled with lava, and unless there's new lava coming in, they will freeze over eventually. And once they freeze over, lava contracts when it cools. It contracts by about 4 or 5%, and then you get these cracks, these contraction cracks, these cooling cracks as we call them, and they are then manifesting themselves as columns, as, well, jointed areas. And if you think of the Giant's Causeway, for example, in Northern Ireland, a famous place with all these magma columns, then you actually see some here. You see these little polygons at the surface. If you were to cut it, you would actually have the same features as had the Giant's Causeway. So the other type, this is also a Hawaiian term, a'a lava, or blocky lava as we call it. And some people say a'a means you cannot walk on it with bare feet. Well, I don't know how true that is. My Polynesian is terrible. But I can give you an indication that it's very crumbly, very spiny lava, and it's very hard to even touch. It's not very good. You shouldn't touch this. And the image on the right is actually from La Palma, where we had this big eruption 2 years ago, and there you see a'a lava creeping into a city. And the city was, of course, evacuated. This is the town of La Laguna, and there we had the lava engulfing even the trees and the street. And yeah, when I sent that picture home, my wife was very concerned about the palm tree. And she said, will it survive? And I said, I don't know. I came back 2 months later, and I had to tell her it did not survive. So it's not so good if you're flown around by lava, you know. So, and here we see another image. This is from Iceland, and there you see that the blocky lava advances in a somewhat different way, and this is often a misconception that people have. It doesn't just flow as a regular liquid, it really works like a caterpillar. And this is that type of lava you cannot stop by digging a ditch. It will actually go over it. And this was a very unfortunate misconception in the La Palma eruption. There was the church of Todoque, and the local people were keen to save the church, and they dug a ditch just in front of the church. If you have the Pahoehoe type lava, it will actually flow into the ditch and flow away. But the AA type lava, which is really like, well, the chains on a tank, it doesn't stop in a ditch. It will overrun the ditch. And the specialists were telling the local people that their efforts are futile. But there was a strong hope that the church can be saved. But of course, it was not. The church collapsed then under the pressure of the advancing lava. So here is the example of that, and here on the right-hand side you see a little house. This was on La Palma, and it was a very strange situation. When I was there, you saw that wall of lava coming, and we witnessed the little house actually collapsing, and I have a video of this, so I'll show this when we talk about the La Palma eruption specifically. So this concept of lava flowing is known for quite some time, and here's some older drawings from Vesuvius, and there you see actually how the different type of lava is changing. In the upper part, the artist here was showing a rather wrinkly lava. In the lower part, it becomes more blocky. So this is a typical phenomenon. When the lava cools, it may actually change from Pahoehoe to blocky lava, and this has been observed, of course, many hundreds of years ago already. So, and here you see similar things, and this is Vesuvius now from the other side. This is actually from the Pompeii side, looking towards the north. And we have this problem today, as I said, human efforts are often dwarfed. If lava comes in these large walls, there's very little you can do. There was this story on Iceland in 1973 at Heimei, and there it was believed that, or the urban legend says that the local fire brigade came with water ships, with fire ships, and they were actually pouring seawater on the lava, and they could stop the lava from filling the harbor. The reality is it was a coincidence. It was mere luck that the lava just happened to stop, because if you cool the surface of this, it doesn't stop the heat inside. And if there's push from beneath, the lava would still advance. There's nothing you can do, really. So, having clarified these kind of urban legends, then actually, let's see, did I put that in? Yes, here we go. Yeah. So, you've seen how it works. So this is us observing this at a safe distance. And the part that was actually not in the video is that just after the house collapsed, there was an explosion, because there was a gas tank in the house, and we didn't quite know that. So it was really like a wartime situation. We were all thinking, oh, the danger is over once the house is, that's myself here stepping carefully forward. But then there was another explosion because of the gas tank in the house. So this is what happens in these situations. And I mentioned Heimei, 1973. Here's a few images from Heimei. This was one of my mentors who was there, Professor Stillman. And I didn't have the pleasure. I was only 2 years of age. So, and here we have the advance from the volcano and the Westman Islands. And here you see the aerial photographs still in black and white. And you see how the harbor basin was about to be engulfed. And this is where the ships came and poured water on it. But as I said, it only really stopped because it wanted to stop, not because of the efforts by humans. So there is usually, as I said, not so much of a danger with these black volcanoes, but there's exceptions. And one of the really unfriendly exceptions was the Laki fissure in 1783. And you see this line of volcanic vents in Iceland. And this was a very unpleasant eruption. The direct effects weren't so bad, but the indirect effects were really intense because it produced a lot of fluorine, and fluorine is not very good for you. A little bit of fluorine is good for your teeth, but too much actually causes fluorosis, and then your teeth fall out. And what happened there was a lot of people starved on Iceland because of this, because the animals ate the grass, and the grass was poisoned with fluor. The animals died, the livestock died, and then the people died. So, and this led to some almost 30,000 people dying on Iceland, and it was actually a large percentage of the population at the time. And in addition, there was poisonous fluorine-rich clouds coming all the way to Europe, to the UK, to Ireland, and even to Sweden. Southern Sweden was affected. And if you go to the church records, for example, in southern Sweden, in Skåne, that's the area, you can actually, if you do statistics on them today, you can actually see there was higher mortality at the time. So Iceland does affect Europe. So volcanoes are an international problem, obviously. So this was black volcanoes, and yeah, there is a few dangers, but overall, they're not the most dangerous of volcanoes. And if they are calmly producing a lot of lava, they build up large shields, and often we call them shield volcanoes, and Hawaii has such a shield. The island of La Gomera here is also a beautiful shield shape. If you look at it from a distance, from Tenerife, for example, you can see that, and it's like a warrior shield on its backside, and that's where the name comes from. This is the largest volcano we know. It's not on Earth. It's actually on Mars. It's Olympus Mons, and it's, well, 70,000 feet high, as it says there, and it's 340 miles across. Why are the volcanoes on Mars so big? Well, it's because Mars has no plate tectonics. So once you have a feeding system of magma and no plates are moving, then you can build up these large volcanoes. Here in the Canaries, as we said, the plate is moving ever so slightly at 2 centimeters a year. We have a stationary magma supply, and the plate is moving away. You make one volcano after the next. But if we were on Mars, all of the Canary Islands would be superimposed on top of each other, making a giant volcano. And that's why Olympus Mons on Mars is so big. So, there is the case of Surtsey, and I need to talk a little bit about that, because black volcanoes, as I said, are usually not so dangerous. But again, there's exceptions, and that is if you have water and magma interacting. And in 1965, this little island formed, Surtsey, and it erupted, and it's still there. Nowadays, there's worries that it might disappear again, because these islands, if they don't continue to produce new rocks, then they will actually, well, vanish at some point. Wind and weather will take them, will grind them down. But this was a big scientific revelation at the time, because it was rather explosive, despite the fact that it was dark basaltic lava. And that is because a lot of the water was converted to steam, and that makes the explosions. We even refer to it as a Surtseyan type, a hydrovolcanic eruption today when we see things like that. So, but now I'd like to move on to the not so friendly volcanoes, the red volcanoes. This is Mount St. Helens in 1980, and these are very explosive volcanoes. So, they have the greatest risk for humans. They often produce pyroclastic flows. Pyro is fire in Greek, and clastic is broken by fire. So there's no continuous flow of lava. What happens is that the material breaks up from gas expansion, and that produces ash and other particles. And these can form glowing avalanches, blasts and surges, as we often call them, and these, of course, have huge destruction potential. The volcanoes in Japan, in Indonesia, in the Caribbean, in the Northwest American Cordillera, and in the Andes are of this type. And the different types of volcanic eruptions show very different hazard potential. So this is why also we have a lot of fatalities in the southern hemisphere, where many of those volcanic systems are. They contrast the friendly, dark volcanoes that we talked about just before. So I'm showing this image once more. Now we're going to focus on the 3 types of eruptions in the left part of that illustration. And we're going to look at Pelean eruptions, Vulcanian eruptions, and Plinian eruptions. How does it actually work? Well, you all had this experience. You have a fizzy drink, and the fizzy drink is in a bottle of, well, in a closed bottle or in a can. And if you shake it a little bit and you open it up, it sprays out. And why does it spray out? Well, it's because there's gas dissolved in the liquid. And once the liquid is under pressure, the gas stays in the liquid. There is no problem. As soon as you decompress it by opening the bottle or the can, the gas will start to expand. And that drives the liquid out, and it actually fragments the liquid. You get a spraying effect. And that's what happens with magma as well. And that produces tiny little particles, pyroclastic particles as we call it. And that is, for example, what then erupts as ash and other types of materials. So it's effectively an overpressured soda can that you may want to think of inside a volcano. Once you take the lid off, it will spray out quite violently. So the first phenomenon I'd like to talk about here is ash fall deposits. And here we have this Plinian eruption, a column of ash and hot gases rising up into the air, and it may go several kilometers high, and then it might spread out when it reached a certain level of buoyancy, and then the winds might also carry it away. So at Mount St. Helens, for example, there was total darkness within 360 kilometers of the volcano at the time during the eruption, because the density of the cloud is so intense that light doesn't come through anymore. The associated ash fall caused, of course, a lot of destruction. Agricultural lands was affected, and if the chemistry of the ash is not very good, then it's a poisonous effect. Basaltic material is usually quite good for agriculture, but the red volcanoes have higher silica, and it's usually not so good for agriculture. So here we then have dry volcanic ash, but if there's rainfall on top of it, the volcanic ash actually turns into a slurry or into a cement type material, and that's extra harmful. So let me give you a few impressions here. This is actually from the Volcano eruption. I don't have sound right now, but actually here I keep it in this is ash fall. Here, a few images from the situation back in 1980 at Mount St. Helens. And here you see the cars in the lower left. This is not snow, this is volcanic ash. And what looks like a snowstorm in the top right is actually volcanic ash being blown around. And volcanic ash is not good for you if you breathe it in, because the tiny little particles, they will stick in your lungs. You will never get them out again, and it can cause silicosis. So the particle density in those situations is so high that you can only really work there with a mask. And back in the 80s, nobody really told anyone about that. So nowadays we know a lot more. So it's not very healthy to be in those situations, and ash fall has severe consequences. So here's a few more impressions of ash clouds back from Mount St. Helens in 1980. And this gentleman here, he was smart enough to put a mask on. But as I said, if we have then ash mixing with water, it becomes like a cement or a concrete. And here we have that letterbox there being, well, partly engulfed by this slurry, and the car driving there, well, it creates an ash cloud in itself. And this means very high particle density in the air, very bad for humans and animals, of course. So here's the ash cloud from Mount St. Helens, and this is the travel speed of the ash cloud. And as you see, it actually traveled almost 1,000 kilometers, and at 9:15 in the morning, it was about 50 kilometers away from Mount St. Helens. And by end of that day, at 18:15 in the evening, it had traveled something like 1,000 kilometers to Idaho Falls. And is, of course, a wind factor here. If the wind comes in one direction, it, well, blows it in that specific direction. If the wind goes another way, if the wind would have come from the other side, it would have blown out onto the ocean and would have been far less devastating for humans and animals in the area. So luck is, of course, the weather in this case is, of course, also a factor that always comes in. So the other thing we see at these volcanoes is pyroclastic flows, and here's a pyroclastic flow from Merapi volcano in Indonesia. And then In the top right image there's a pyroclastic flow deposit from Augustine Volcano in Alaska. And this is hot ash clouds that rush with enormous speed down the hillside. They're usually valley hugging. They usually follow low ground, and they would travel in ravines, for example, but they can be up to 600 degrees hot, and they travel with up to 500 kilometers per hour. There is no escape if this is coming towards you, and that makes them very, very dangerous. So here's one of the very first pyroclastic flows ever observed from Montagne Pelée in 1902. This was after the disaster of Montagne Pelée in 1902. The French scientists, they came there and they were puzzled what happened to the city. They had no idea. And then later in that particular summer, 1902, another one of those ash clouds came down the hill, and Lacroix, he made that photograph, and this was one of the first realizations for modern science that this is a phenomenon. Prior to that, we really had no idea. And then we have Pinatubo in 1991, for example, and my understanding is that this car did not make it. So I've mentioned the eruption on 1902 from Montagne Pelée in Martinique, in the Antilles. And well, Saint-Pierre, the city, it was believed to be, or it had the reputation of being the pearl of the Lesser Antilles. It was the local capital. It was beautiful. And there was an election coming up, and the political elite was very keen to not evacuate the city to make sure that the election would go through. There was good signs we would recognize today as being very dangerous. There was good signs the eruption was imminent, but the authorities did not evacuate the city. In contrast, they invited all the refugees from the villages into the city. And what happened then was that a huge ash cloud traveled down at several hundred kilometers of speed with temperatures probably over 800 degrees C, and it devastated the city. So on the left here in the bottom, you have a photo just in the days before the eruption with all the ships in the harbor, and then on the right-hand side, not a single house survived in Saint-Pierre, and 30,000 people died. And later in the summer, Lacroix took that picture, and that explained what actually happened, that such a hot ash cloud was traveling very rapidly down from the volcano through the city and killed all the people. So here's a few impressions from Montagne Pelée eruption 1902. There was a lot of warning signals. The wife of the American ambassador actually writes in a letter home that the conditions were terrible. Horses are collapsing in the streets because of the sulfurous smells and the ash, but that was not enough to evacuate the city at the time. So it led to this catastrophe. And worse yet, as you probably know, Martinique produces a lot of rum. And after the hot ash cloud went through the city, all the rum distilleries were starting to burn. And rivers of burning rum have been reported at the time. So it sounds a bit crazy, doesn't it? But obviously there was no preparations for a volcanic eruption at the time. Often, these are the kind of very tough lessons that help us to improve things enormously. And of course, today we have a very functional volcano observatory on the island that is manned 24 hours a day, 24/7, and it checks exactly what the volcano is doing. So, Mount St. Helens, this is something that has also been a bit of a surprise at the time, and therefore an amazing lesson for volcano researchers. So what happened here was, here's a time sequence, it's only minutes here. We have the volcano bulging out initially, and then the volcano actually collapsed. And we talked about large landslides here in the Canaries, and actually Mount St. Helens had such a landslide. And the landslides uncorked the volcano. In the central image, you can really see the flank of the volcano moving, and then the eruption started, not the other way around. So there was, if you will, an uncorking effect by gravitational sliding of the volcanic material, and then the big eruption happened. And this was the big eruption cloud at Mount St. Helens that has been recorded, and it killed several of the volcano observers that were stationed there. And two of the heroes of volcanology are these two gentlemen there, Truman and Johnson. And one was stationed 2.5 kilometers, the other one 4 kilometers away from the volcano. And they, believe it or not, they actually buried their cameras underneath them. And we were able to retrieve the films in the cameras. So they took images until it was just about too late, and then they turned around. So once people realized what these gentlemen actually did, it was really recording for science until the very last second possible. So, and here is the trees surrounding Mount St. Helens, and actually it looks like a big devastated forest, but still there's use for volcanologists because the direction in which the trees have fallen actually tells us how the clouds were traveling. So we can use that to map the progress of the ash clouds. So this is Mount St. Helens today, and there's a new dome growing inside, and there is a little stippled line, and it shows you the size of the volcano prior to the collapse, and of course all of that material is missing. It's been blown into shreds, and that was causing the big eruption and devastation around Mount St. Helens. Another effect there at Mount St. Helens was not only the direct eruption, there was another thing, and that is mud flows. And here on this specialist map, we don't need to go into details, but there you see in dark colors in black the debris avalanche from the ash and pyroclastic cloud, but then you also see along the rivers that it says mud flows. And this is another problem because they happen to come a little bit later after the eruptions. All the ash is lying around, and then it rains, and then you have slurries of ash-rich mud, and it travels down the rivers. It's basically like concrete flowing down the rivers. So there's a new dome growing inside the crater of Mount St. Helens, and this is from an image from 2006 when I happened to have a chance to look at it. And this is now pushing up, and it's a little bigger now actually, and it's still growing. So sooner or later in geological time, Mount St. Helens will fill its peak up again. So let me bring you to Indonesia now, and this is where the death toll of volcanoes is a lot higher. And I mentioned Merapi volcano earlier. Merapi volcano is called a killer volcano for good reason. It killed about 1,500 people in the last few hundred years, and it's almost permanently active. It has a few breaks every now and then, but it's continuously erupting, and there's a lot of people living around the volcano. The city of Yogyakarta, with 4 million people, 3.5 to 4 million people, is only about 20 kilometers away from the volcano. So this is Merapi, and there we have several UNESCO World Heritage sites like the Borobudur Buddhist temple, the largest Buddhist temple in the world. And it was actually only rediscovered about 150 years ago. It was buried under ash and lahars, mud flows in the jungle. And the British colonial forces heard about it, and they sent an expedition out there, and they actually discovered it, and now it has been reconstructed. And it sits at the foot of Mount Merapi. So this volcano has quite a history. This is where I got involved as a young researcher. I was able to join the efforts at the time in 2006, and this is the village of Kali Atem, only about 6 kilometers, 6,000 meters away from the peak. In the top right image, you can just about see the peak of Merapi in the background. The village was evacuated, but it didn't survive. 2 volcanologists were stationed at the time in an observatory bunker, and the bunker was buried. And these 2 gentlemen did not make it out. So this is the dark side of volcanoes. These things are very, very severe, and this is now a volcano park. You can go there. The village has never been repopulated. So here's a few more impressions, and the image in the bottom with a gentleman in the yellow t-shirt, that's the observatory bunker, and this is where the 2 observatory staff found their last well. So we have large eruptions of this type also in the Canaries, and this is a succession of large volcanic ash cloud deposits on Tenerife, in the south of Tenerife. Luckily, no such thing happened for about 200,000 years on Tenerife, but back in its heyday, in its early days, there was large eruptions. You see the thickness of these ash and pumice deposits. They're quite massive. And they would really wipe out everything in its way. And science is, of course, partly opportunistic. And when you look at these deposits, you find all sorts of things in them, including fossils. So we found the skeleton of the giant canary rat in these deposits. That's a species that's now extinct, and you can see some of these fossils in the museum in Santa Cruz in Tenerife. And yeah, so for science it has been very useful, like Pompeii in Italy has been very useful for understanding Roman life, but of course for the people or creatures involved, this is not a very nice end. So I'd like to talk a little bit about indirect effects, and we mentioned it already, mud flows. Lahars is the technical word, it's an Indonesian word, and they can be cold, but they can also be warm, depending on what type of water you have involved. And usually you have a lot of granular particulate material from volcanoes that mixes with water. The water can be rainwater, can be glacial water, if you have a little bit of ice on your volcano and it melts in the heat. And it can also be all sorts of other surface water, river water, etc. So, and once you have this mix, it makes the material very, very dense. It makes this liquid very, very dense. It's got the density of concrete, and it flows, however, very much like water. So you have these rivers of dense mud traveling at reasonably high speeds down into channels, into riverbeds, etc. The most unfortunate case in recent history was the Nevada del Ruiz eruption, where the town of Armero was affected. And this was actually well understood that this is a risk. There was a bunch of USGS, US Geological Survey people there. They did the hazard assessment, and they had maps that were supplied to the mayor of the town of Armero saying the town is at risk from major mud flows. But the mayor put the map into a little cupboard and ignored it. And then the eruption happened, and within hours, a major mud flow came out from the hills, from the mountains, flowing down and wiping out the city of Armero, 70% of the population perishing in that event. So here's a few impressions of the aftermath, and this was Armero in 1985. And actually, if you, well, you can't quite see it, but if you look very carefully, this is an old alarm clock, and they had these little dials there back in the day, and you could actually see the time when the event happened from that alarm clock. So as I said, this was all known, and here in the upper panel, we see the hazard map established by the USGS, and they have clearly marked the dark brown areas being riverbeds as being a risk for lahars, for mud flows. And indeed, when the eruption happened in the lower panel, this is exactly what happened. So just knowing about the risk and understanding them is not enough. You need to really do something about it. So another disaster with a mud flow goes back to the 1950s in New Zealand, the Tangiwai disaster. And I was in New Zealand earlier this year, and I visited the site. This is the memorial there. What happened there was Ruapeu volcano, the largest volcano in the North Island of New Zealand. It had a breach of the crater lake, and there was a mud flow coming down in the middle of the night. It was actually Christmas Eve. And it took out a bridge just before the Auckland-Wellington Express was coming towards that bridge. And well, the train didn't have a bridge anymore, and it partly went into the valley that was under the bridge. However, there was a very strange situation. One of the local people, he saw this and he tried to warn the train driver with light signals, and the train driver actually realized something was wrong, so he put on the brakes, but it was too late to save the entire train. So half of the situation got bad, but several of the carriages were actually saved. So not everybody died, but 151 people perished in the event. So this is the bridge today, and it's not even a very deep river, it's a very small river actually, but it's enough if you have a whole train with several carriages running into that without a bridge to support it. So this is the crater lake of Ruapeo, and it looks quite benign up there, but there's a lot of snow, as you see. There is also sulfurous water, and this was the material that came down, taking a lot of ash with it and taking out the bridge further down. So again, if you look at the area surrounding a volcano, then you see that these deposits are found all around Ruapeo. So Ruapeo has a record of doing this. This is how a deposit from a large lahar would look like. It's a mud flow with loads of boulders and finer particulate material. And this is actually how these things would look like. Imagine this being liquidized, fluidized, and running down a riverbed. There's virtually no stopping it. So, tsunami, I want to talk a little bit about tsunami. And tsunami is, well, a Japanese term because they have a lot of these waves coming. And they actually come from Hawaii. And often the flanks of the big Hawaiian islands, they have some landslides, submarine landslides, and that creates big waves, and they travel all the way across the Pacific to reach Japan. And this is why Japan has a lot of these problems, and the Fukushima disaster, where the tsunami hit the power plant not so long ago, is part of this problem. So tsunami, they are forming from submarine earthquakes or from submarine volcanoes more commonly, and massive flank collapses of volcanic islands would cause tsunami, and the Pacific is very prone to having tsunami. And in 1883, Krakatau erupted, and it produced a big tsunami as well, killing some 36,000 people, and almost 300 villages in coastal areas were destroyed. So this is a big problem. And not enough, in 2018, Krakatau erupted again and produced another tsunami, killing another 400 people. So we are still not really good at this. This is still a big problem out there. So this is Krakatau, and this is an artist's impression of the volcano prior to collapse, and then the remnant of the volcano, Rakata Island, in the lower image there. So you get a sense. Maybe the upper drawing is a little oversteepened for my flavor, but you get the idea. Much of this volcano collapsed, and there's this report of this Dutch steamer, the Barrow, and the Barrow was actually caught by the resulting tsunami wave and was now found almost 2 kilometers inland. It was swept into the jungle, and there it's still today. You see the image in the lower right. This is where the Barrow is today. I actually asked an Indonesian colleague recently what happened to the Barrow, and he says, oh, the local people have taken a lot of the iron now to work it. And the last I heard was there's a monkey colony now living in the ship. So this is Krakatau, and a new volcano grew, Anak Krakatau, the child of Krakatau, and it grew inside the caldera complex. And this new volcano in the bottom right, you can see it, collapsed again, as I said, in 2018. And in the top right, you see the outline of the volcano prior to the collapse and what's currently left there. And these volcanoes are very unstable, they're very explosive, and if they are sitting, for example, in the ocean, they actually cause devastating water waves, and they can, of course, devastate the surrounding. And the image in the middle bottom is the travel speed of the tsunami in minutes. And here you see within about 2 or 3 hours, it reached the city of Jakarta, and there the tsunami was still measured. So, having talked about this, there is good evidence that there was a big tsunami here as well in the Canary Islands, several in fact. If you look at these anomalies here, these are actually giant landslide scars, and they would have made big tsunami when they collapsed, when large chunks of the islands broke off, falling into the ocean. Then you get a severe splash, and well, you can make some calculations. Some of these waves may well have reached across the Atlantic all the way to the eastern seaboard of the US, for instance. So, and the biggest scare that we have in the Canary Islands is the island of La Palma. It's volcanically very, very active. It had large landslides in the past, and there has been big media row about 25 years ago, and here's a few of those headlines there, about potentially a collapse of La Palma happening. And the calculations of the scientists at the time said there will be a giant wave reaching Florida if that happens within less than a day. Now, how real is that? Well, there was a big eruption just 2 years ago, and the island did not collapse. So I actually think we're pretty safe. It's very unlikely that the island will collapse very soon. But the real issue, the real debate started with that crack that I'm showing here in the central image. This crack opened up in the 1949 eruption, and it would allow the speculation that part of the island could break off and fall into the sea. But we had not just the 1949 eruption, we had the 1971 eruption and now the 2021 eruption, and nothing happened. The island is stable. There's also monitoring equipment now. There's no movement on that flank. So this crack may have had a very different reason. It may not necessarily imply that the island will collapse right away. But can we be sure it will never collapse? No, we can't. At some point it might. But the probability is super, super small. It's very tiny. So I don't think any of us will actually witness a giant collapse in our lifetime. So this is the calculation, and this is from the original article about the travel speed. And the numbers are very, very small, but there it's about 9 hours, and then the wave would hit Florida in the bottom right hand on the right hand in the right hand image, and then there's an artist's impression here of this giant wave hitting the city. I personally think the wave may not be quite that tall, but well, geologically we cannot exclude that this will happen again. So then a few words just at the end about volcanic hazard and the mitigation. And here's a postcard from Seattle when I was there a few years ago. I liked that postcard with Mount Rainier looming in the background there, and it gives you a sense of a very vulnerable society close to a big volcano. And I just talked to a gentleman a few minutes ago at the beginning of our little session from Mexico, and there's of course places like Popocatépetl next to Mexico City, 30 million people in Mexico City, and there's a big volcano right next to it. Whew, it makes for a lot of very fertile land. This is good in a way if you live next to a volcano, as long as the volcano does not erupt. So, what do we do? What can we do? Usually it requires very careful monitoring, and it means long-term monitoring. It's not good enough to just check on your volcano every now and then on a Sunday afternoon. You really need to look at your volcano every day. You need to have 24/7 monitoring, surveillance out there. So, and what we usually have to do is we have to establish a baseline. What does the volcano do when it's calm? Because only then can we recognize if something is changing. So that requires us to really spend time and logically also resources at our volcanoes. So less favored region, financially less prosperous region, can often not afford such long-term surveillance, and that is partly the reason why we have a higher death toll in countries that have lower income on average. So one of the first volcano observatories is actually this one here, the Osservatorio Vesuviano, and you see Vesuvius volcano in the background. Then we had the 1920s, seeing, for example, the Palaean Volcano Observatory, the Hawaiian Volcano Observatory, and then in the 1930s, the early Indonesian observatories were built up at the time, mainly from the Dutch colonial administration, and then later they were, of course, taken over by the Indonesians, and this is providing us with long-term monitoring. The 1871 Vesuviano Observatorium, this was merely a chap with, some binoculars looking at the volcano every day, every hour, making a note. And then, of course, increasingly, there was photographic evidence and things like that. And now we're more and more technical about how we monitor volcanoes. So this is an image from Indonesia from the 1930s where photographs were taken, and there certain phenomena were recorded, and there was actually a very good record that now allows us to go back and say, oh, there's a certain rhythm to certain volcanoes. Even the information is, of course, not as good as we would do it today, but we still can learn a lot even from fragmental records at the time. So I happened to visit the old Vesuvius Observatory, which is now a museum. There's a newer one closer by, and the Italians gave me that wonderful little field vehicle in the lower left. I thought it was a terrible kind of thing, but yeah, I never had another Fiat in my life. So, here, this is what we do at Volcanoes. So here, we're monitoring active volcanoes with many different methods today. We're checking at the seismicity. Does the ground shake? We're checking does the tilt. Does the ground actually deform? Does it bulge up? We look at it with cameras. We look at the temperature. We see whether the water in the area is suddenly having more sulfur or having a higher temperature. We're checking this. The thermometer in the top right here, it's in a fumarole at an Indonesian volcano. You may just about be able to see it. It says it's over 200 degrees hot. And it's maybe a little too small, but in the top right of that image, there's actually a little bit of liquid sulfur. And liquid sulfur usually requires some 250 degrees centigrade. So this is kind of giving us indication. And if that changes, we will make a note of that. So nowadays we also increasingly use remote sensing. We don't always have to go there, and there we can, for example, check ground deformation with satellites, and there's an image, a radar interferometry image in the bottom right that gives you these fringes when the ground is moving, and this shows, oh, something is bulging up, for example. So usually we check different parameters. We check expansion, we check seismicity, we check gas, temperature and chemistry, but also heat flow in, for example, aquifers in the region. And usually we expect all of these parameters to change if the volcano is waking up. So we have different specialists looking at these, and if several of them say, oh, we have an issue, something is changing, then you need to get alert. And then you need to think about, how long will it take? How dangerous is the situation? How many people will be affected, etc., etc. So, volcano monitoring, therefore, looks at a whole range of things, a multi-parameter approach, and we're looking at all of these different things that I'm listing here. I mentioned most of them, and this is what observatories do. They observe these changes, if there is any. So, this is what I mentioned, radar interferometry. These days, we're looking at things remotely as well as on the ground. We have boots on the ground as well as all sorts of remote sensing. And remote sensing is, for example, also a temperature method these days. We can, with satellites, actually see any thermal changes. This is Merapi in Indonesia. And you see when it was waking up, in the crater area, you see the colored pixels. And that tells us, oh, there's heat coming out now. So you don't actually have to go into the crater anymore. You can actually see that there's a change remotely. Then we can also work out how ash clouds travel. This is Etna, and this is from the ESA, the European Space Agency. And there you see not just the cracks in the lavas, and you also see the direction with which the ash is traveling, and this allows you to make a calculation which areas will be affected downwind from ashfall, from, well, low air quality, etc., etc. So, and this goes further. This was one of the earliest scenarios where this has been applied. This was an eruption in Alaska, Mount Spur, and there we see the colored ash and gas cloud coming from the spur, and here you see the travel speed, and if you know the weather and the wind direction, you can actually see how the material is traveling, in this case all around the northern part of the US and Canada. So this then allows people to be warned in time about low air quality, gas in the air and things like that. So after the Mount St. Helens eruption in 1980, which was a bit of a shock for everybody, the USGS really put a lot of effort in, and there was another eruption 2 years later. And nobody really knows about this eruption because it was completely non-spectacular. because the USGS did their homework and they were able to predict the eruption within 2 hours of its event. And here they have mapped the seismic energy, the dome expansion, the tilting of the flanks, and the SO2 emission. And all of these parameters were pointing towards the same thing, allowing them to say, there will be an eruption tomorrow at 12 o'clock. And then it was at 1 or so. So, and this is of course the same for the Canary volcanoes. This is an image in the right-hand side of the volcano on La Palma. And this was in the exclusion zone. People were not allowed there. Only volcanologists could go that close. And in the bottom left, I'm showing the seismic activity. The eruption is the stippled line. And there was quite some evidence for the volcano waking up, actually in the weeks before the eruption. But scientists knew already 3 years before that something was in the bush there. The local population, of course, didn't really realize this, but the scientists knew an eruption was going to happen sooner or later on La Palma. So this is now satellite imagery from La Palma as well, and this is just in the days up to, leading up to the eruption. And here you see these fringes again, radar interferometry. You see these fringes showing that the ground was swelling up, and just where they all culminate, there we had the eruption center. So these methods even allow us to say partly where the volcano might actually erupt, where the vents will be. So this hopefully puts you at ease. All the Canarian volcanoes are monitored. So we will find out if there's an eruption. And the good news is we're going to Fuerteventura tonight. Fuerteventura did not have a volcanic eruption in at least 130,000 years. So we're all good, I think, and can enjoy the rest of our trip, and I thank you for your attention.